want to take a look at our electromagnetic radiation mini-assignment that we handed in yesterday in preparation for our test that we have tomorrow. We start off with a pretty challenging question. Maybe we should have started off with something a little bit easier to kind of get you into it, but it is what it is. First question says, students use three of the optical apparatus illustrated below to produce a focused real image in a darkened room. That's important. So important, in fact, that they bold it. It's a focused real image in a darkened room. One of the apparatus is a focal length of 10 centimeters. Okay, that's pretty important as well, that we have a focal length of 10 centimeters. When I see this real image and I look at all of these different apparatuses, 9 different apparatuses, there's a bunch of them that I can cross off right now because there's a bunch of them that will never produce a real image with a focal length. First of all, a double slit apparatus or a diffraction grating, there's no focal length associated with that stuff. So if we're talking about a focal length of 10 centimeters, it's got to be a lens or a mirror, right? It can't be a diffraction grating or a double slit apparatus. It cannot be a diverging lens or a diverging mirror or a plain flat mirror because all of those in every single case produce a virtual image. Now, that's not to say that a converging lens or a converging mirror always produce a real image. They don't, but they will sometimes. Diverging and flat mirrors never produce a real image. So it can't be those ones. It could be 2, it could be 4. Okay, we'll try both of those. What else are we going to have? Well, if we want to produce a real focused image, we're going to definitely need to use a screen. Okay, this is a done deal. We've got to use a screen. If we want to produce an image of an object, technically we could use either one, a laser or a candle. I would have, if I was writing this test, absolutely picked the candle. Okay, but this was keyed to accept 0 or 1, object 0 or 1, the laser or the candle. The candle produces an image that's a candle, a flame. The laser produces an image that's a focused dot. Okay, I would have definitely picked the candle, but you would have gotten credit for this if you had to pick option 0 as opposed to option 1. So we got 3 apparatuses that we want to use at location X, Y, and Z. One of them is going to be, we're going to say object 1, but you could have replaced that with 0. It's interchangeable. One of them is object 9, and the other one is going to be either 2 or 4. So we got 2 things to worry about here now. We got to worry about whether we use the lens or the mirror, and we got to worry about where we put them, the positions we put them in. Here's the way I started off myself when I did this. I always do the question, and then for some of these, I had answers that they've provided. For some of them, I didn't. This one I did. When I do this, I'll check my answer with what they have and see, make sure I've done it right, or to make sure that they've done it right. I put my object right here at location X. And you know what? I did next what you guys, I think all of you did next. And that is said, I think it's going to be a lens. I think it's going to be a converging lens, object number 2. And if object number 2 is going to be right there, then the screen, object number 9, is going to be right there. Well, that's going to produce a real focused image, right? But what about the distances? Do the distances work out here? Turns out they don't. 1 over F is equal to 1 over DO plus 1 over DI. The object distance in this case is 15. It goes from 5 to 20, so the object distance is 15. The image distance is from 20 to 35, so it's also 15. 1 over F becomes 2 over 15, or F becomes equal to 7.5 centimeters. That doesn't match up with what they told me. They said the focal length was 10. So this doesn't work. A convex lens or a converging lens doesn't work here because in order for the distances to be the same as we've got here, position X, Y, and Z, the focal length would have to be 7.5 centimeters, and it's not. It just doesn't work. So I think we can eliminate this. Let's try the concave or converging mirror now. If I'm going to try the converging mirror, I'm not going to put the mirror right here. and the screen right here, you're never going to get a real image in behind the mirror. You will in behind a lens, but to get a real image with a mirror, it has to be in front of it. It has to be on the same side as the object. Think about your ray diagrams. Go back to your ray diagrams. When you had a real image, it was always produced over here somewhere in front of the mirror. So if this is going to work, it's going to have to be like this. The object reflects off of the mirror, produces an image over here. Turns out if it does produce this image, it would be underneath the principal axis, so it would be down here. The screen wouldn't necessarily need to get in the way. Let's check out the numbers here just to make sure that this works out. Okay, we think it's got to work out. Listen, if it doesn't work out, I'm not sure what we're going to do, because we've eliminated all of these all these diverging things. We've eliminated the flat mirror. Okay, we've eliminated the diffraction grating and double slit because they don't have a focal length associated with them. Okay, if this doesn't work out, I don't know what we're going to do. 1 over f is equal to 1 over do plus 1 over di. My object distance here would be from 5 to 35. My object distance would be 30 in this case. My image distance, if this works out, would be from 20 to 35, so my image distance would be 15. Now, you can do this on your calculator. I'm not going to bother hauling out the calculator for this one because it's easy to do, fairly easy to do with a common denominator, but it's 1 over 30 plus 2 over 30. 1 over f is equal to 3 over 30, and f works out to be 10. Would you look at that? That's exactly what they told me in the question f was. This works, doesn't it? So the answer for this question was, at location x, it would be 1. At location y, it would be 9. At location z, it would be 4. We would accept 1, 9, 4. We would also accept 0, 9, 4. The laser, the converging mirror, the screen. This is what I got for my answer, and those were both keyed correct. What I didn't anticipate, what I missed when I did this, was 2 more possible answers. I would have got this right, but I missed 2 possibilities that were also correct answers. Anybody want to take a quick stab at what they were? Couldn't you have used 5? Well, you wouldn't use 5 and go the opposite way, because 5, if you take a look at that, you're on the right track, though. Right? This is a diverging mirror. Okay? Any way you look at it, whether you flip it upside down or whatever, it's a diverging mirror. Okay, the smooth side is the reflecting side. So you'd flip over the mirror, right? And it's still going to be a diverging mirror. So you'd still use objects 1, 4, and 9, or 0, 4, and 9, but you could do it as 4, 9, 1, or 4, 9, 0. Okay, because you could have went from the other side. I just didn't think of that. Which was okay, because I would have got the right answer if I was doing this on a test, but there were 2 more possibilities that you guys could have done, and you got marked correct that I didn't anticipate, that's all. Does that make sense? That's a tough question, hey? That's a real tough question, especially the first one to start off an assignment, but you know what? It's a good question to start off an assignment with. If it's a test, maybe not so much so. If it's an assignment, it's a great question. It gets the juices flowing, gets your mind going, and hey, you get your test tomorrow, and all of a sudden, most of the questions aren't going to be as challenging as this, and it makes it easier, right? Hopefully, at least it makes it easier. Hopefully, it makes the diploma exam easier as well. All right, next question. Next question was a little bit different as well, though it wasn't nearly as hard. It was a little bit different. We had to measure the angles here. We measured this angle, most of you measured this angle to be 31 degrees, although some of you measured to be 32. It did kind of appear to be a little bit above, sorry, the other way around, right? This one was 31 or 32. It kind of looked to be a little bit above 31, I thought, approaching 32. So what do you use, 31 or 32? I said 31. Okay, I said 31. Now this one, I thought was pretty clearly 39 degrees. Okay, I didn't think there was too much ambiguity with that one. I thought it was exactly 39 degrees. If we use Snell's law, say sine theta 1 over sine theta 2, sine 39 over sine 31 equals n2 over n1. N1 was, I think, 1.33. We solve for n2. I forget what the value we get exactly, 1.63 or something like that. Okay, 1.63. That was the most common answer, and that's what I would have got personally as well, was 1.63. But the range of answers that they accepted on the exam, the Alberta Ed people, was 1.54 all the way up to 1.69. So basically, if you said 32 degrees there instead of 31 degrees, you got away with that. Okay, it was good because it was a little bit ambiguous. Okay, and if you ever saw something like that on an exam, there would also be that range. You wouldn't need to panic. Oh my goodness, is that? Oh, it looks like it's a little bit above 31, or is it a little bit below 32? Do I use 31 or 32? It doesn't matter. You're okay in either case. Okay, don't ever sweat that. I mean, somebody in the last class said 30. Well, that's wrong. That gives you a number, an index of fraction, I think they use 30 and 40. And I think that gives you an index of fraction of 1.71, which almost was acceptable. But that's two angles that were clearly wrong. Okay, if you measure them carefully, they're clearly not 30 and it's clearly not 40. So you got to be careful of that. You can't just put any angle around what it is. Okay, but if it's a little bit ambiguous, you don't need to worry about it. 31, 32, either way. When a girl is 122 centimeters tall, that's HO. She stands 40 centimeters in front of a mirror. That's going to be DO. Her virtual image, I'm going to underline that or circle it, her virtual image. Okay, that's going to tell me that it's a negative DI, even though I don't know what the number is yet, so I'm not sure that I really need it to circle that, just in case. Her image is upright and 54 centimeters tall. We're going to call that HI, and it's going to be a positive HI because the image is upright. We want to know what kind of mirror it is. We want to know where her image is located. Hey, if I want to find DI, I got two equations with DI in it, right? 1 over F is equal to 1 over DO plus 1 over DI. I've also got HI over HO, the magnification equation. HI over HO equals negative DI over DO. We're going to drop the M part of that and say HI is 54 over HO, which is 122, equals negative DI over DO, which was 40. And I think we needed that DI worked out to be negative 18, wasn't it? Is that right? Her virtual image, look, I get a negative value for that, so it's telling me, look, I'm probably right. I got negative 18. We know it's a virtual image. The negative agrees with that. That means the answer is either going to be A or C. How do you know whether it's a concave mirror or a convex mirror? A converging or a diverging? Okay, good. Okay, that's one way. A convex or diverging mirror always produces, if you think about your ray diagrams, it always produces a virtual image, which is what we have here, but it always produces an image that is upright and not smaller. No, it is upright and smaller, isn't it? Yeah, it is upright and smaller, which doesn't help us there, actually, because that's an upright and smaller image as well. Sorry? But how does it help us? Oh, I see what you mean. Yeah, I see what you mean. Yeah, no, I see what you mean. So convex mirror. Yeah, absolutely. I'm thinking about the wrong thing there. A convex mirror produces an upright and smaller image. That's what I've got. A concave mirror can also produce a virtual image. But when it does produce a virtual image, the image is bigger, right? And we don't have a bigger image there. So if you think of it that way, answer A, good. If you can't think of that, if you can't think back to your ray diagrams or you don't want to sketch them, whatever, solve for the focal length. 1 over F is equal to 1 over DO plus 1 over DI. Okay, I don't know what the focal length works out to be there, but I can tell you the focal length will work out to be work out to be negative something. And if it's negative something, then that tells me that it's got to be a diverging mirror or a convex mirror. Is that good? Answer is A. Classical wave theory, quantum physics make different predictions about the effect of incident electromagnetic radiation on a photoelectric surface. Classical physics, right? Newton, Hertz. Hertz is the relevant guy in classical physics here, right? Because he's the guy that tried to explain the photoelectric effect. So whenever you see classical physics in the context of the photoelectric effect, we're thinking Hertz. Usually classical physics is defined as pre-1900, pre-20th century physics. And then quantum physics, Einstein, Compton, de Broglie, quantum physics, lots of guys with quantum physics. But in the context of the photoelectric effect, quantum physics would be Einstein. So basically, we're trying to match predictions up with either Hertz or Einstein. Low intensity EMR, incident on the surface for a long time, will cause the emission of electrons. Think back to the demonstration we did in class with the balled up pieces of paper here. Okay, throw pieces of paper at, who do we throw it at? Parker. Throw it at Parker. Okay, one piece of paper didn't cause an ouch, right? 100 pieces of paper doesn't cause an ouch. So if we're low intensity and low frequency and it's not happening, okay, then it doesn't matter how long we do it for, it's not going to happen. This isn't true. Well, if it's quantum physics, it's true. Okay? Must be classical. Must be part of Hertz's explanation. High intensity EMR will not cause emission unless its frequency is greater than the threshold frequency. Hertz or Einstein? That's definitely Einstein, right? Quantum theory. The energy of the electrons will increase if the intensity will increase. No. Okay, the energy of the electrons increases only when the frequency of the photons increases. That's classical theory. And the energy is independent of the intensity. Yeah, because it's dependent upon the frequency. That's going to be quantum physics. So we're going to say classical is 1 and 3. Quantum is 2 and 4. Now they say there's more than one possible answer. What are the other possible answers? 1, 3, 2, 4. 3, 1, 4, 2. 1, 3, 4, 2, 3, 1, 2, 4, right? Different combinations of these, right? I'd like you just to double check your answer to make sure that you didn't have a different combination there. There was a couple people in the last class that I marked wrong that were right, that said 3, 1, 2, 4. Okay? All of those work out. You just can't put 3 over here in quantum physics or 4 over there in classical physics. The order of them is okay within these circles, but just outside of the circles they have to be the same. Okay, this one was relatively straightforward. You guys did a real good job on this one. We've got an angle. This is a diffraction experiment problem, right? A Young's double slit experiment problem. Okay, you've got, although it's done with microwaves, usually it's visible light. Okay, you've got an angle here. You've got receiver placed 52 centimeters from the grating. That's going to be L, the distance from the grating to the screen, basically. First order maximum at positions 1 and 2. We're going to say N is going to be equal to 1 because we're measuring it from the central. And what else do we have here? Something else we have here. Yeah, D, the distance between the openings there, 1.80 centimeters. We're just going to say lambda is equal to d sine theta over n. We got to use this equation because the angle is huge, way bigger than 10 degrees, right? Okay, let's plug our numbers in there. And when we do, we end up getting, if we convert it to meters, we end up getting 0.0137 meters or 1.37 times 10 to the, 1.37 centimeters. They want you to express the answer in centimeters, so let's go with 1.37. Michelson experiment. Hey, listen, when we did this, I told you a couple of things. First of all, it's very recipe-based, right? We do the same thing every time. You don't really have to think real hard about these. You got to be able to do it. You got to know what you're doing. But if you can do it, you can do it for all of them. Second thing is, this has appeared on just about every diploma exam since this became a part of the curriculum. So odds are it's going to appear again. We don't know for sure, but odds are it's going to appear again. I can tell you that if we have something that appears on almost every exam, it's going to appear on your unit test. So expect to see this on tomorrow's unit test, for sure. Okay, something like this. Okay, we know that every time we see one of these questions, we start off with two equations. V equals d over t, t is equal to 1 over f. This is the time for 1/8 of a rotation. This is the time for one complete rotation. We start plugging numbers in. The speed of light is 3 times 10 to the 8. The distance is 60,000 meters, not 30 kilometers, 60,000 meters. And we solve for the time here. Okay, remember we said we solve for whatever you can solve for. I don't know what that is because I don't have my work in front of me on this page, but whatever it works out to be, it's not the time we want. What do we got to do with it? We always got to get the other time, right? It's always, the grass is always greener on the other side of the fence. Okay, we get this time, we want the other one. We get this time, we want the other one. What do we got to do to get the other time from this? Abby? Times it by 8. Okay, careful, don't divide it by 8 because we were already at 1/8 of revolution. Times it by 8, and we get big T. Plug the value of big T in there, solve for the frequency. When we do, I'm going to tell you right now it's going to be 625 or 6.25 or 6.25 times 10 to the 2 hertz. Okay, I know that because A, I have the answer in front of me right now. B, I know that because I calculated it. C, I know that because, or at least I can make a pretty good guess that that's the right answer because what did I tell you in class the frequency almost always is? If you're dealing with numbers that are Nicholson-like numbers, 35, 30 kilometers, 8 sides on the mirror, we're almost always going to end up with 10 to the 2. Yeah, 10 to the 2 hertz. Okay. If this is a question that you're leaving till close to the end of the exam, or it's question number 50 on the exam, and the teacher says, time's up. Okay, this is a question you can get right by guessing. I don't want you to have to guess because it is possible to get another number there, especially if these numbers are different. It's possible, but usually we're going to end up in that 10 to the 2 range, okay, 90% of the time. So you got a real good chance at getting that correct even by guessing. You got a better chance if you know how to do it, but you got a real good chance even by guessing. Okay. Only guess if you have to, though. And what distance above this page would a convex magnifying lens be? Oh my goodness, another hard question. This, I think, was the second hardest question on the page. Some people might have even argued that it's the hardest. We're looking for DO. We got a focal length of 10 centimeters. We got a magnification of 3. And it's a positive 3 because it's upright. That's all we got. We want to find DO. Look at that. Got F, got M, want to find DO. Let's try 1 over F is equal to 1 over DO plus 1 over DI. Let's try that. Don't know if it's going to work. 1 over 10 equals 1 over DO. Don't know that. 1 over DI. Don't know that. Okay, that wasn't helpful. Let's try this. M is equal to HI over HO equals negative DI over DO. Let's get rid of the HI and the HO because they didn't appear anywhere in here. That's not going to be helpful. I know that. Negative DI over DO. 3 is equal to negative DI over DO. Uh-oh. I only have 2 equations, and I got 2 unknowns in both of them. But those 2 equations have the same 2 unknowns. So therefore, let's do this. Let's go back to math class here now. It's a tough one. But let's go back to math class and say DI is equal to negative 3 DO. All we did is rearrange that and solve for DI. Got that? Take the value of DI and plug it in here. We're going to say 1 over 10 is equal to 1 over DO plus 1 over negative 3 DO. That doesn't make me happy when I see that, but it makes me happier because at least I see one unknown in one equation. Now, it doesn't look pretty to solve for, but we'll see what we can do. Let's take it over here just to make some more space. 1 over 10 is equal to 1 over DO subtract 1 over 3 DO. Okay, same thing, right? Same deal there. 1 over 10 is equal to 3 over 3 DO. Think about that. 3 over 3 is the same as 1 over 1, right? 3 over 3 DO minus 1 over 3 DO. Oh, now it's coming. 1 over 10 equals 2 over 3 DO. Now it's doable, right? Take the DO up by multiplying. Take the 10 up by multiplying. And I end up solving for DO, and it works out to be 6.67 centimeters. All right? Tough question, eh? I'd be surprised if you got something that was quite as mathematically tricky as that question was, but it's possible because this was a diploma exam question. Okay, if it was a real diploma exam question at some point in the past, you never know down the road, right? Now the math gets way easier. Still some challenging questions ahead of us, but the math is easier at least. Satellite in orbit around the Earth is exposed to radiation from the sun. The radiation may cause the satellite to become positively charged. Platinum is commonly used to coat satellites that have a work function of 8.5 times 10 to the minus 19. If we're talking about a work function, we're talking about the photoelectric effect. Electrons ejected. What happens when an electron is ejected? The surface is going to be, well, it's got one less negative, so it's going to be positive. Which of the wavelengths listed above would cause a satellite with a platinum coating to become positive? In other words, which of the following would cause an electron to be ejected? Now we're going to solve this. Listen, in order to cause an electron to be ejected, and that's what we got to do to make this positive, we got to be above the work function. So let's find the energy of each of these. E is equal to hc over lambda. Get the energy. I don't know what they are because I don't have them all written down in front of me, but get the energy for each of them. If they're above the work function, electrons are ejected. It causes the surface to become positive. If they're below the work function, then electrons aren't ejected. The surface stays where it was, and it don't cause the surface to become positive. When you do that math, you find that, let's see here, numbers 1 and 2 are both above the work function. The energies are both above the work function. Therefore, will both cause electrons to be ejected. Therefore, will both cause this surface to become positively charged. 5. EMR constant wavelength is incident on a metal cathode. We want to know the relationship between the maximum kinetic energy, the max kinetic energy, and the intensity of the EMR. Intensity is related to the number of photons. The kinetic energy is related to how fast they're moving. There is no relationship between the number of photons and how fast the electrons move. If the number of photons doesn't affect the kinetic energy, then this would be our answer right here. Now, in the last class, I pointed out another graph that you could conceivably see. What if it said the electric current in the intensity? Well, the intensity is related to the number of photons. The electric current is related to the amount of charge, the number of electrons. Is there a relationship between, as long as you're above the threshold frequency, the number of photons and the number of electrons ejected? Yes, there is. So this graph would look like this. If we changed this to electric current, then all of a sudden, that becomes our correct answer, right? Almost done here, guys. We'll come back to this one, number 6, actually. Number 7 says, what's the maximum frequency of an X-ray that can be emitted by an electron that has a kinetic energy of 2 times 10 to the 4 electron volts? Hey, look, we haven't talked about electrons causing X-rays, so on. So how are we supposed to do this question? Hey, in the end, where does the X-ray get its energy from? The electron. So the maximum energy that the X-ray can get is 2.0 times 10 to the 4 electron volts. If the X-ray has that energy, then it's going to have this frequency. So it gets its energy from the electron, set them equal to each other, solve for the frequency. When you do that, number 7 works out to be B. Number 8, we want to know the wavelength of this satellite here. We got a frequency. in megahertz, the wavelength is just v is equal to f times lambda. Lambda is equal to v over f. V is 3 times 10 to the 8. And the frequency is 1575.42 times 10 to the 6. Do the math there. Worked out to be B, I believe. Yep, 0.190 meters. The last question, we will go back to one more here. But numeric response number 5 says the time that it takes the signal to go from the satellite to the Earth. This one's just V equals D over T, even easier. The distance was, I think, 20,200 meters, or 20,200 times 10 to the 3 meters, 20,000 kilometers, 20,000 times 10 to the 3 meters, divided by 3 times 10 to the 8. Do that math, and it worked out to be 6.73 times 10 to the negative 2 seconds. Finally, let's go back to this one. And this one's a good question to go over. Let me tell you, this one's a good question to go over right now. The reason being is because it's real closely tied to what we've done this unit. In fact, we're real closely tied to what we've done over the last couple of days, right? Compton effect. It's Compton scattering. This is what this is. But it really takes us back to early on in Unit 1, momentum, right? Look, we got a collision between an electron and a photon. We got a funny angle here of 85 degrees. Let's get rid of that first of all. We got a momentum here of 1.72 times 10 to the negative 23. We've got an x component. We've got a y component. Let's get the x component using cosine. Let's get the y component using sine. And then let's do x's and y's for pi equals pf. You guys remember this from back in Unit 1? Pi equals pf. We're going to say m1 v1i plus 0, because the electron's at rest, equals m1 v1f plus m2 v2f. But we don't really have m1 and m2 because one of them is a photon. So what we're going to say is m1 v1i is the momentum of the photon, 1.83 times 10 to the negative 23, plus 0 equals m1 v1f. Whatever you got for the x component there. m2 v2f, it's whatever the final momentum of the electron is. Solve for the final momentum of the electron for the x component. Do the same thing for the y component. And then what do? Combine them using the Pythagorean theorem, right? For the y component, the initial momentum would be 0 because it's all x-axis, equals the y component that we just found here plus pf. Solve for pf. And then recombine them. Does that make sense? That's a real good question to go over right now, because it's been a while since you've done conservation of momentum in 2 dimensions, and you never know when you're going to have to do a question similar to that again.